Hi everyone, welcome to Bond Energy Calculations 1 walkthrough. So I'm going to be showing you how you hopefully answered the Bond Energy Calculations 1 worksheet that I set last week. So for this first question, we've got hydrogen reacting with bromine to make hydrogen bromide. So the worksheets helpfully set it out for you in parts A, B, C, D and E to guide you through the stages in order to calculate the energy change and then talk about why the reaction is either exothermic or endothermic. They've given you the data that you'll need at the top of the worksheet. So the first thing you want to do is look at how many bonds are breaking out of our reactions. So we're going to be breaking this hydrogen-hydrogen bond and this bromine-bromine bond. So then from our data at the top of our worksheet, we can see that a hydrogen-hydrogen bond is 436 kilojoules per mole and our bromine-bromine is 193 kilojoules per mole. So altogether our bond breaking energy is 629 kilojoules per mole. We then turn to the product side of our reaction to see what bonds are made in this reaction. So we've got a hydrogen-bromine bond, but as we've got two molecules that are formed, we're going to be making two lots of that HBr bond. So the energy that would need to be released when those products are made is going to be two lots of the HBr energy of 336, which is 732 kilojoules per mole. So then to do our energy change, we do our bonds breaking, so 629, as this is our endothermic positive process, subtracted by the bonds made, so that minus that 732, as that is our exothermic negative process, and so we get an energy change of minus 103 kilojoules per mole. So that minus sign tells us that it is an exothermic reaction, and reasons for that in terms of bond breaking and bond making, we can say that more energy is released when bonds are made compared to the energy required to break bonds. And that's all we have to do for that first question. So moving on to number 2, identifying what bonds we are breaking. So we've got some CH bonds. We've got 1, 2, 3, 4 of those CH bonds. We've got a C-C double bond, just the one of those, and we've got one Br-Br. So then, looking at our data at the top of our worksheet, we're going to be doing 4 times the bond energy of CH bond, which is 412, and we are going to be doing one of the C double bond C, which is 612, and then one of the BRs, which we've already seen, is 193. So adding those all together is 2,453 kilojoules per mole. Now looking at the bonds that we're making, we've got some CH bonds that we're making here. We've got 1, 2, 3, 4 of those CH bonds again. So again we're going to have that 4 times 412. However, this time we've got some CC single bond, just the one of those, and we've also got 2 CBr bonds. So looking at our data sheet, that CC single bond is 348 kilojoules per mole, and our CBr, which we need 2 lots of, is 276 kilojoules per mole. So adding these all together, and we get our making energy of 2,548 kilojoules per mole. And so again, when we're doing our energy change, we're doing our bonds breaking, so that 2,453 kilojoules per mole subtracted by that 2,548 kilojoules per mole, and we end up with an energy change of minus 95 kilojoules per mole. We have a minus sign, and therefore it is exothermic. Our explanation is going to be identical to our one for question 1, so I'm just going to say C question 1, as it's an exothermic reaction, so we're still talking about more energy being released when bonds are made compared to the energy required to break those bonds. So question 3 now, bonds breaking, hydrogen-hydrogen and a chlorine-chlorine. So looking at the data at the top for those bond energies, our HH is 436 kilojoules per mole, and our ClCl is 242, and adding those together we get 678 kilojoules per mole, whereas our bonds making is an HCl bond in each molecule. We've got 2 molecules, so 2 of those HCl bonds are being made, so 2 lots of 431, which is 862 kilojoules per mole. So our energy change, bonds breaking 678, minus our bonds making of 862, gives us an energy change of minus 184 kilojoules per mole. Again, it's negative, therefore it's exothermic, and as it's exothermic again, our explanation can be the same as what we've written for question 1, more energy being released when the bonds are made compared to the energy required to break those bonds. When I was writing this out, I mistook number 4 for number 5, so just swap over to this page and we'll come back to number 5. Just want to make sure it's all in order for yours. So question 4, we've got some double bonds here, so SO, SO double bond. So we've got 2 of those in one molecule, however we have 2 molecules of this sulfur dioxide. So 2 lots of the 2 gives us 4 of those SO double bonds. Here we've got 1 O double bond O, and so just looking at our data sheet for those bond energies, so we've got 4 lots of 435 for the S double bond O bonds, and we've got 498 kilojoules per mole for our 1 oxygen double bond. So adding these together and we get 2,238 kilojoules per mole. Turning now to our bonds that we're making S double bond O's. This molecule has 1, 2, 3 of those S double bond O's, but we've got 2 molecules of it, so we're going to do 2 lots of the 3, which gives us 6. So 6 lots of that 435, which gives us 2,610 kilojoules per mole as our bonds that are being made. So our energy change, we're doing our bonds breaking minus our bonds making again. So 2,238 minus 2,610. And this gives us an energy change of minus 372 kilojoules per mole. It's negative, therefore it is exothermic. As it is exothermic, we can say C question 1 for our explanation. So bonds breaking, we've got some CH bonds. So 1, 2, 3, 4, 5, 6, 7, 8 of those CH bonds. And then we've got some CC single bonds, so we've got 1, 2 of those. And we've also got some O double bond O's. Each molecule of oxygen has one of those, but there are 5 molecules, so we want 5 lots of that one. And so now we can look at our data. So 8 lots of the 412 for our CHs, 2 lots of the 348 for our CC, and 5 lots of 498 for our OO. So adding these all together, and we get 6,482 kilojoules per mole. And now turning to our bonds making, we're making C double bond O. Each molecule of carbon dioxide, CO2, has 2 C double bond O's, but we've got 3 molecules, so we want to do 3 lots of that 2, which is 6. And our water molecule, we've got 2 OH bonds per water molecule, but we've got 4 water molecules, so we want to do 4 lots of that 2, which is 8. So then looking at our data for these, so we've got 6 lots of 743 and 8 lots of 463. Adding these together gives us our bond making energy of 8,162 kilojoules per mole. So we can now calculate our energy change. 6482 minus 8162, and that gives us an energy of minus 1,680 kilojoules per mole. It's negative and therefore it's exothermic, and therefore we can say C question 1 for the explanation. Turn back the page so we can go to question 6, looking first at what bonds we are breaking. So we've got some CH bonds, so 1, 2, 3, 4, 5, 6 of those CH bonds. We've got 1 single CC bond, and we've got 1 C double bond C, and here we've got 1 BR. So looking at our data for these, we're going to have 6 lots of our 412, 1 lot of the 348, 1 lot of the 612, and 1 lot of the 193. Adding these all together, and we get 3,625 kilojoules per mole. And for our bonds making energy, we need to look at what bonds we're making. So we're making some CHs. So 1, 2, 3, 4, 5, 6 again. So we're going to have that 6 times 4 and 2 again. We've got more single carbon bonds here. So 1, 2 CC bonds. So we're going to have 2 lots of that 348. And we've also got some CBr bonds being formed. So 1, 2 of those CBrs. Looking at our data for the CBr, we're going to be doing 2 times 276. Adding these all together gives us 3,720 kilojoules per mole. So our energy change here, our bonds breaking, 3,625 minus our bonds making 3,720, and that gives us an energy change of minus 95 kilojoules per mole. It's got a negative sign, therefore it is exothermic. And our explanation is C question 1, as it's to do with more energy being released when our bonds are made compared to when our bonds are being broken. So now we're moving on to final question, question 7. So looking at our bonds that are breaking, we've got some CH bonds in both of these molecules. So we want to add both of these together. So 1, 2, 3, 4, 5, 6, 7, 8. Lots of those CH bonds. We've got some CC single bonds in the first molecule. So that's 1, 2 of those. We've got a C double bond O in that first molecule. And then we've got a CO in both the first molecule and the second molecule, so 2 of those. And we've then got an OH in the first molecule and the second molecule, so we want 2 of those. So looking at our bond energy data for these, we're going to be doing 8 lots of 412 for our CHs, 2 lots of our 348 for our C single bond C, 1 lot of 743 for our C double bond O, 2 lots of our 360 for our CO single bond, and 2 lots of the 463 for those OHs. Adding these all together, and we get 6,381 kilojoules per mole, and our bonds that we're making, we're again making some CH bonds. So 1, 2, 3, 4, 5, 6, 7, 8 of those again. So it's still going to be that 8 times 412. And then we've got some CCs, 1, 2 of those, which is going to be our 2 times 3, 4, 8. We've got that C double bond O, and so that's 743. We've got a CO and another CO. And then we've got 2 OH bonds in the water molecule. And what you are probably already spotting is that we have exactly the same bonds in our reactants as we do in our products, and our energies when we add them all up are exactly the same. So our energy change, 381 for our bonds breaking, minus 6381 for our bonds made, gives us an energy change of 0 kilojoules per mole. So here, it is neither exothermic nor endothermic. And that is because we are having the same amount of energy is released when products are made, as the amount of energy required to break the bonds of the reactions. And that is all. If you want any further explanation of any of these or anything that you didn't understand, please do just drop me a message and I will do my best to explain those to you. Thank you for watching, and I hope you're keeping well.